presentation, right?
Yes.
Good.
Great. So hi, my name's Eugenia. I'm a PhD candidate in the chemistry department at Northwestern. And today I'm going to talk about solar energy and solar cell technology. And here I have a picture from a university in Switzerland where they've put solar panels on their window sort of as a dual purpose to like generate electricity, but also to have like a curtain with the sun. And it's they're actually like multicolored, which we can't really see here, but it's a pretty image. Okay, let's get started. So I'm going to talk about sort of some major milestones that were important in solar cell technology, some basics of how solar cells work, and then some more specific things about solar cell technology or PV. So PV, photovoltaics, solar cells are synonyms. We can use them interchangeably. And I'm going to talk about like what solar cells are being used now and what is sort of being developed in lab, which is called the next generation. And this is where my research is in. And then some data and trends. So
Mary, how are you?
Hi, we're going to watch this together.
Good. Here, turn it around.
No, I can
So
see
you
it
can
here.
see it?
So yes, a little bit about me. I was born and raised for the first 10 years of my life in the LA area of California. And then my family moved to, let's see, to Greece. In the city you see here with a green, which is called Thessaloniki. It's popularly known.
Moved to Greece.
Oh.
Because of Alexander the Great, who was from the region. And here we can see sort of a picture of a statue. And then we have a view of Mount Olympus across. So pretty area. And I graduated actually my undergrad degree there at the Aristotle University. So here's a picture with my family at graduation with the statue of Aristotle, who was also from that area. And then I came to beautiful Chicago to do my PhD. And at Northwestern, here's a picture of me with one of my favorite lab instruments called an X-ray diffractometer. And here are some of the samples that I make that are materials with potential for solar cell applications or other electronic applications.
Yeah.
So what are we going to talk about today? About solar energy. So what solar energy is trying to address as a proposed solution is the industrial development and population growth have led to this surge in global demand for energy in recent years. And this results in a so-called energy crisis, where a lot of wide range environmental problems have also emerged. And this is a reason for a push towards renewable energies.
I don't know who, but they're having a program at 1 o'clock.
So when we talk about sustainable energy, which solar energy is one of those kinds of energies, we're talking about an energy that is meeting the needs of the current generation without compromising the ability of future generations to meet their own needs. And solar energy harnesses this energy from the sun that's sort of free to take in and convert it into electricity. And although there's a huge technical potential and large-scale development of solar energy technologies available, there are still financial and technical barriers to overcome in order to have this as a mass increase in energy supplied from solar cell systems. So the future of manufacturing and research is to lower the costs, have better policies, and improve the design of these technologies. Okay. So let's go down memory lane of some important milestones for solar cells to be developed. So in 1840, this French physicist Edmond Becquerel first observed what we call the photovoltaic effect. So this means that he observed that in a material, when you hit it with light, it's able to generate current voltage. And so a few years later, Wilby Smith observed this in some other element, but then Einstein was who was the first to be able to sit and make sort of a theory and equations and formulate scientifically what was being observed. And he won the Nobel Prize actually for this reason. So even though we know him for the theory of relativity and all those great things, he actually won the Nobel Prize for studying the photovoltaic effect. So then in this time period, we can remember that transistors revolutionized the field of electronics, and they are part of our electronics even to today. And so physicists at Bell Laboratory were able to use the element silicon, which was being used in these transistors, to create solar cells with an efficiency starting off with 4 to 6%. So this was a huge breakthrough, and this sort of was the first important milestone in the like true application of solar cells. And sorry, and so over the next few years, the government funded solar energy technology for the use in space exploration, space satellites. And then shortly after, in the 1960s, Hoffman Electronics was able to start providing solar cells to the market for consumers, reaching an impressive efficiency of 14%. I also should mention, when I say efficiency, I mean, so from sort of the light that hits this material, the sunlight, 14% is converted to electricity. And so that may not sound a lot, but it's actually an important amount. So this is, where these were the major milestones. So I'm going to be using a word called semiconductor a lot. And what I mean with this word is a material that can generate electricity when it's hit with light. And thankfully, we have here Mother Nature, which has given us these different elements we can see. And there are semiconductors that can be used to be highlighted in orange. So as I mentioned, silicon is the one that has been developed the most. But there are other materials, there are the compounds with different properties that we can either use by themselves or in combination. So we would love to explore these as semiconductors for solar energy as well. So how do solar cells work? I have this 3-minute video. Emily, I don't know if, I guess we can have time to watch it. It's 3 minutes. Okay, so then I should stop sharing this and I should say, I hope that audio will be, is it here?
We can give it a try.
Okay.
What the heck?
Can you guys hear?
I think so, yeah.
Okay, cool.
Oh, thanks a lot. You're welcome.
I don't think I'm hearing the audio anymore.
No. Oh, really? Interesting. So it was in the beginning, but not afterwards?
I thought I heard it at the beginning.
It's
Okay.
10:22 right now.
I'm wondering
We got
if we do full screen. Share.
Take care.
Is something being heard? No? Okay,
No.
that's all right.
Bummer.
I'll just talk about this. Okay, let's go back to share. New share. Okay, so essentially everything around us, the air, we have these particles called atoms, and inside there are sub particles called electrons, which are negatively charged, and holes, which are positively charged. And so when light hits these materials, if they're able to sort of generate this electron hole pair and be able to separate it, then we can generate electricity. And so a solar cell is one of these squares, and when you get the squares all together, you have this bigger thing called a solar panel, which is what we see being used and housed on rooftops and whatnot. And so, yes, and this goes back to what we talked about, the photovoltaic effect. This is the main scientific principle of how solar cells work. And as we're saying, one of the main things is we want to have a high efficiency. We want all the sun that hits these materials to be transformed into electricity. So finding materials that can do that very well is a big goal of research in this field. So, okay, so when we talk about solar cell photovoltaic technologies, we talk about different generations. So first generation is what we talked about in the sort of historical milestones, which was the development of silicon solar cells, and they are the ones that are being used now commercially. So when we look at houses or commercial solar cells, they have the first generation silicon developments. Now, second generation thin films are the ones that started being developed more recently in the last, I guess, 20, 30 years, 40. And these have just entered commercialization status. And then emerging or next generation, which is the third generation of solar cells, are the ones that are still in research. So maybe we have some devices at a research stage, but they have not yet been commercially available. So this is what we mean by first, second, third generation. So as we've talked about, we are currently using in the market the first generation photovoltaics with silicon. And silicon can be used, can be processed in different ways to make a solar cell. So monocrystalline silicon is the most efficient, but it's the most expensive. Why is that? Because it's the most homogeneous. That's why it's the most efficient. So you have a material and it has the same properties all over its whole length and its whole length. So that's a good thing, right? If we have different defects or different variations, that's going to change the overall performance. So multicrystalline silicon is sort of like that. It's not super homogeneous, but it's much more cheaper to process. So that's why that's a good advantage. And then we have thin films. So these are pretty much taking this material silicon into very, very thin layers, which is why we call them thin films. And so they're less efficient because, as you can imagine, you're having less material, but they're very cheap, right? Because less material, less time and money to process. So these are sort of the different forms of solar cells that are being used. And here is a graph of sort of the different types of solar cell silicon solar cells that have been used in the market from 1980 to 2016. So the light blue is the monocrystalline silicon, the one we talked about that is homogeneous, most efficient, but most expensive. And then the multi-silicon is the one that is less efficient. And then we have thin films that are the newer technology. So we can see how over time, the cheaper technologies are starting to gain more use and are slowly eclipsing the monocrystalline silicon, which is more expensive. So as I talked about, this is the first generation solar cells. Like, why did we want to go on to second and third generations? Well, the thing is, silicon is great because it's very abundant, it's not expensive, and it has a great efficiency. So it's reached an efficiency of around 25%. However, the thing is that silicon is not the most efficient compound or material that researchers have observed. But the thing is that we use it because the technology has been well developed. As I've talked about, it's been studied for around 50, 60 years. And it's sort of like when we cook and we have a recipe, right? Like, I think each of us has that recipe we know how to make very well. So we're going to make that because we know it and there's not difficulties. We're not going to have unexpected things happening. But if we really want to increase efficiency and have a greater solar energy production, we want to think about seriously these disadvantages, which is mostly the fact that it's not the most efficient material and that it does have expensive processing. So with that, I'm going to talk about the third generation, the very new sort of research, which is what my research falls under, and sort of talk about some elements that we think about. So again, I'm showing this great periodic table. And so the elements are there. We just need to understand them and develop them. So it's not discovering new materials, it's more of developing new materials because they're there. We just need to understand how they work. And so for solar cells, we want, as I talked about, single crystal because that's the most homogeneous. You're going to have the same properties around along the whole material. And we want to have thin layers because that's least expensive and easier to make. And it'd be great if this was cheap and not very expensive. So I'm showing here how silicon looks in single form and sort of the processing to become a solar cell. And then I'm going to talk about, now I'm going to show you guys perovskite solar cells. So this is the materials I work with. And so perovskite is just a fancy way to talk about the structure's pattern. So if we like had them, if we could see every sort of we can see the structure of this material at a super in-depth nanometer eyesight, we would see the arrangement of atoms like this. And so we can make big crystals, and we can make very easily thin crystalline layers. And so it's great because the maximum efficiency already in the last 10 years that this material has been studied and developed has reached 22%, which is competitive to silicon. But as I talked about, this is still a next generation, third generation material. So it's not commercially available yet, but it is being developed in research. And so here I also thought I'd talk about what I do in lab, and sort of emphasize how these materials are low cost in processing, because I go into lab and I use very cheap starting materials, and then I can make these different crystals you see here. And then these crystals can be processed very easily by cheap solvents at low temperatures to make these films that can be used in solar cell applications. And so here's a picture of my research group, and we have sort of reported high efficiencies in this class of materials, which is very promising and exciting. So next I want to, and then I just wanted, this is very sort of a lot going on here, but I just wanted to show, like, from 1975 to 2010, all these other colors are silicon, which is like reaching very high. And then here at the very end, if you can see, sorry, it's quite small, the red is sort of showing these third generation materials, where in like the last 10 years, they've reached efficiency that is comparable to silicon, which has taken around 50 years to reach a high efficiency. So with that, I also wanted to talk about some trends in the US market of solar. So here, this was from 2016, and it's showing how in the last few years, solar energy has increased, solar cell panels have increased around, I think, 70% in installation. And but even though there's been this huge increase, they only solar energy accounts only for around 3% of the US electric generation. So there's still a lot to go forward in increasing the share of solar energy in the electric generation of our country. So I also want to show what other countries are doing. So here is a map of some countries that have a large solar energy production. And sort of Germany seems to be the lead here. And why is this? So for reference, in 2014, Germany reached a significant milestone because it was able to satisfy reportedly 50% of its electric demand by solar energy. And if you think about it, Germany is not really known for the sunshine. So for reference, they get around 1,800 sunny hours per year, whereas in the US, Yuma, Arizona, which is our sunniest region, gets around 4,300 sunny hours a year. So how were they able to sort of have a huge electric generation based on solar energy? So it's a combination of strong public support and political will to pass necessary regulations to start using solar energy. So in the 1990s, German politicians sort of had these renewable energy acts. And so with that, the industry knew that they were being firmly backed by the government. And so investors were confident to make long-term investments. And so this helped financially stabilize the market. But I just want to show how this is even more possible in the US to happen, and even greater, because we can see here a map sort of the amount of sunshine regions in the US have in comparison to here, where it's Germany and Spain. So Spain is like a country we think about that's pretty sunny, and then Germany is not a very sunny country. But even though they're on the lower end of irradiance that they get yearly, we can see that what I've talked about, they have a high production. So it's more than possible and even better for us to do that here in the US. And so, and the data shows, sorry, that solar energy is increasing, as I showed. So in the last 7 years, 40% of all new electric capacity came from solar, which was the largest in history so far in the US. And the cost has also dropped. Yes, so I also wanted to talk about how the cost has dropped. So an average sized residential system would cost pre-incentive price around $40,000 in 2010, whereas now it can be roughly around $20,000. So that's very promising, and that's sort of what we want. We want to have policies and investors sort of put their focus on this so it can become cheaper for us consumers. And so here is a map of the top 10 states in 2017 that had solar PV capacities, and California was at the top of this, but it's actually very promising because in the last 2 years, we can see a large increase in PV installations across the country, with California, Arizona, Texas, and Florida being the top places where installations happen. So if we look at our own state here in Illinois, we're ranked around 21st in solar cell installations in 2019. So around 45,000 homes are powered by solar. And this accounts for 0.21% of our state's electricity. And there's been around $750 million investment. And the prices over the last 5 years in Illinois have decreased by 40% for solar installations. And there's been a growth projection over the next 4 years for Illinois to from 21st to be 14th among the US in solar power. So we also want to talk about the fact that this technology also helps create new jobs. So in early 2019, around 250,000 Americans had jobs in the solar industry. That was double the amount in 2012. And we can see here that the main employment in solar is in installation project development, which accounts for 65% of jobs. So the pandemic has sort of hampered the predictions of increase in PV installations in the US, which have, since the impacts have been greatest in the residential and commercial segments, which historically rely on in-person sales strategies. So there's supposed to be an 11% decrease from the residential commercial installation forecasts that were made. But as I talked about, we can be positive because we've seen a great increase in this technology in the US over the whole country. And so then I briefly wanted to talk about the solar investment tax credit, which is an important federal policy to support the growth of solar energy in the United States. So it was enacted in 2006, since then, it's been able to create thousands of jobs and investment of billions of dollars in the US economy for this process. And so this data I've been showing you is from a group called the Solar Energy Industries Association, and they've been successfully able to advocate for a multi-year extension of this credit, so it can provide critical stability for business and investors. And so despite the overwhelming popularity and success of the ITC, the value of credit will unfortunately start decreasing after 2019. So like it's started to decrease. And so what this means is that the dollar for dollar reduction in the income taxes that a person or company would otherwise pay by the federal government, that tax credit will start to decrease. And so that isn't very great, because that means that the certainty for companies to develop long-term investments and drive competition and technological innovation will sort of not be as competitive or as quick. So yes, so the outlook based on what we want is we're trying to develop new materials that can be lower in cost, have greater engineering in the installation and design. And we also want to think about policies that could sort of subsidize this and help people be able to use this technology, which, as we talked about, is sustainable and good for the environment. So with that, I would like to thank you, and I'm happy to answer any questions that I can.
Thank you so much, Eugenia.
You're welcome.
I have a question.
Yes.
Yeah.
On the campus of the University of Illinois, Urbana-Champaign, we have a solar farm. I drive by it often. How can I tell what kind of solar farm it is just by looking at it? I mean, they just look like ordinary old panels, but I noticed that in your research, they were curved panels that you were working on.
Yeah, that's a great question. So I think because those are in the first generation, so they're probably films of silicon, but you're right. It's difficult to understand if they're like from monocrystalline silicon or multicrystalline. That's, I guess, something we have to like ask Google. But they would be sort of in the first generation of materials that have been processed as films, because those are the cheaper ones that are used in applications that we see. But then again, because it's a university campus, they might have more niche technology. Yeah. So they could be maybe also like the more expensive kind. But yeah, I think that's a great question. And either, I guess, asking or looking it up would give us a definite answer.
Yeah, that's good. Yeah, I could just go by and ask, right? Anyway,
yeah.
Question. You have lots of interesting graphs there. Do you have anything that?
Hello.
I'm on the.
Oh, I'm sorry. I just wanted to bring you the lunch special for today.
Right.
I'm sorry.
It's lunchtime.
That's good.
Do you have a graph that would show the extent to which solar is taking over from nuclear or hydro or other sources of
oh, that's a great question. I think I didn't include that, but I did, or was that in the, so here we're looking at natural gas, coal, wind, and other. Yes. And sorry, what was your question about this?
Well, I assume that solar generation is taking over from other sources of power generation. So, for example, is nuclear is that market being reduced somewhat, or how about hydro, or of course,
right.
you know,
great question. So from here we can see the solar, natural gas, coal, wind, and other. So I'm going to assume in other they're putting nuclear and I guess hydro. And it seems like that is being reduced as solar and natural gas seem to be increasing, and wind sort of. So yes, those seem to be decreasing in use.
Yeah, okay, thank you. That's great.
Yeah, thanks so much for these thoughtful questions.
I have a question, Eugenia. Who's usually buying solar panels? Is it usually like companies? Is it like the government? Is it like individual families just being like, I want to put a solar panel on my roof?
That's a great question. I think I also saw some graphs about that. I think it's a combination of companies and homes, I think. Although I'm not 100% sure. But there's definitely, when I was researching this, there were graphs about that. Yeah.
Gotcha. That's really
so this website, where is it? CEIA, they have like they do this like every year. They like try to generate data. And so, yeah, they definitely have data on that.
Very cool.
This is sort of just a side question, but I noticed at the beginning of your talk, or maybe, were you from Thessalonica?
Yes, yeah.
You know, there's a famous guy who wrote letters there. Paul
Really?
wrote his letters to the Thessalonians.
Oh, yes, correct. Exactly.
Throw that in.
Yeah, so I had a video to show about the city, and so sort of show like from antiquity to medieval to modern times. And so, yeah, there's a lot of history there.
Yeah, certainly. One other thing that's just a minor editorial thing, but at the very beginning of your talk, you talked about PV, but since that's not my field, it took me a while to figure out what that SOL stands for, photovoltaic.
Oh, yeah, correct. Yes. Yeah, it was, so I wanted to use one, either solar cell or PV, photovoltaic,
Right.
but then it got sort of, I think like photovoltaic is more the European style of saying it, where we say solar cells. So yeah, thank you though. That's a great point. I should make it homogeneous among the whole presentation.
Well, that was a wonderful presentation, and your research. How far along are you in your research? What's your?
Yeah, so I'm in my 4th year out of around 5-6 years.
Okay, great.
Yeah,
Very
thank you
good.
so much.
Yeah. Thank you for
All
that.
right.
It was great.
All right. Sorry, I've been listening in my office as I'm working.
Yeah.
Great questions, Ken. I think that is really good feedback